All right, my name is Dong Song. I'm a professor at UC Berkeley and also the founder and CEO of a startup called Oasis Labs. Today, I will talk about AI and security, challenges, lessons, and future directions. As we all know, deep learning is making great advancements. For example, AlphaGo has won over world champions. And also, we have already seen that deep learning is empowering everyday products. On one hand, we are seeing this exponential growth of the power and deployment of deep learning technologies. On the other hand, in another landscape, in the landscape of security, we are seeing another trend. Unfortunately, we are seeing that attacks are increasing in scale and sophistication. For example, in recent attacks, hundreds of thousands of compromised IoT devices has caused one of the biggest distributed denial-of-service attacks in history, causing over 1 terabit per second combined attack traffic at its peak. And also, we continue to see really large-scale data breaches where attackers steal sensitive information about hundreds of millions of users in these incidents. And also, attacks are entering new landscape, including the power grid and our banking system. So as we deploy machine learning, we need to consider the presence of attackers for a number of reasons. First, history has shown that attackers always follow the footsteps of new technology development, or sometimes even leads it. And also, this time the stake is even higher with AI. As AI controls more and more systems, attacker will have higher and higher incentives to compromise the AI learning systems. And also, as AI becomes more and more capable, the consequence of misuse by attackers will become more and more severe. When we consider machine learning in the presence of attackers, there are two main types of issues that we need to consider. One, we need to consider how attackers may attack the AI systems. There are a number of different aspects how the attackers may attack the AI systems. First is integrity. For example, attackers can cause the learning system to not produce the intended or correct results. And the attackers can even cause the learning system to produce a targeted outcome designed by the attacker in a targeted attack. Attackers can also attack the confidentiality of the learning system to try to learn sensitive information about the individuals through the learning process, through the entire learning process. To address these issues, we need to develop better security in learning systems. On the other hand, attackers can also try to misuse AI. For example, they can try to misuse AI to attack other systems, for example, to find vulnerabilities in other systems and devise new attacks. And furthermore, attackers can try to misuse AI to attack people, as we have seen in deepfakes and fake news and so on. To address these issues, we need to develop better security in other systems. So first, let's take a look at the first aspect, how attackers may try to attack the integrity of the learning systems. To see why this is important, first let's look at a motivating example. When we consider self-driving cars, a self-driving car, as it drives through the environment, it's very important that it needs to be able to observe the environment. For example, to recognize traffic signs and to help it to make correct decisions. So here are some example photos of traffic signs, real-world traffic signs. And here you can, in the second column, you can see it's a photo of a real-world stop sign in Berkeley, where you can see there are some stickers actually on the stop sign. Today's computer vision system actually can recognize these photos of real-world stop signs very well and recognize that they are stop signs. However, what if attackers actually put maliciously constructed perturbations, such as these stickers on the traffic sign, and they are specifically designed to fool the image recognition systems. And in this case, these adversarially perturbed images are called adversary examples. And in these examples, you see here, these adversary examples are specifically designed to fool the image classification system, and in this case, to cause the image classification system to give the wrong label. In this case, speed limit sign, 45 kilometers an hour. So adversary examples are very easy to construct in the digital world. One question that my group and my collaborators have been exploring recently is whether these adversary examples can also be effective in the physical world. Unfortunately, our study has shown that adversary examples can also be very effective in the physical world, and can remain effective under different viewing distances, angles, and conditions. So these are examples of the actual physical adversary examples, the manipulated traffic signs that one viewed from different viewing distances and angles have all been able to fool the image classification system, in this case, to give the wrong classification. To further illustrate the point, now I'm going to show you a video. So in this video, you are going to see two frames side by side. And throughout the video, you'll see the car is driving towards a traffic sign at the end of the road. And at the bottom of each frame, you are going to see the classification label given by the image classification system. And for these two frames, one frame has the, in one of the two frames, the traffic sign was the original traffic sign without any perturbation. And in the other frame, the traffic sign has been adversarially manipulated. So we are going to do a quick quiz after I show the video. You can tell me which frame contains the adversarial example. Okay, so the video is playing now, and you can see the image, the classification labels given by the image classification systems. So now, can you tell me which frame contains the adversarial example, the adversarially perturbed traffic sign? To your, I guess, it's to your right-hand side or it's to your left-hand side? Let me play again. Okay, so let me just play once more. Okay, so what do you think? Which one is has the adversarial example in the frame? To the right or to the to your right or to the left? So actually, okay. So actually, it's right. It's to your right. So as you can see, so actually to humans, you can see that it's a stop sign, but in the right frame, you can see that throughout the entire driving process, the image classification has been fooled to give the wrong prediction label, the speed limit sign. So this is an example illustrating why it's really important that we ensure that the learning system is resilient against attacks. As you can see, attacks like this can have severe consequences. So my group and also the research community has done a lot of work in this space, given the importance of the problem. Unfortunately, what we have found is that adversary examples are not unique to image classification systems. They are prevalent in deep learning systems. So for example, we have studied for generative models, deep reinforcement learning, all these deep learning systems can all be vulnerable to adversary examples. And also for other tasks beyond image classification as well. And also adversary examples can also be effective even under different threat models where attackers may not even know the details of the target learning systems. So let me just quickly give you a couple other examples to illustrate the points further. So here we are considering a task called the visual question and answer VQA. So in the VQA task, the system given two inputs. One is an image, and the other one is a text. Here, what is the woman feeding the giraffe? And the learning system taking these two inputs will produce an answer. In this case, it produced the answer carrot, which is a correct answer. So in this study, we studied the state-of-the-art systems for VQA. And we wanted to see whether the state-of-the-art VQA systems are also vulnerable to these adversarial example attacks. So here are some of the results from our experiments. So here you'll see that a question, what is, where is the plane? And when given this benign image, the VQA system can give the right answer wrong way. So now the question is whether we can generate an adversarial example version of this benign image by just adding really, really small adversarial perturbations to try to fool the VQA model to give a different answer, in this case, to give the target answer sky. So here's the generated adversarial examples. As you can see, this generated adversarial example to human eyes looks really similar to the benign image. But however, when we feed this adversarial example to the VQA model, it produces the targeted answer sky, the wrong answer. And here's another example. Here's a question, how many cats are there? And when we feed this benign image to the VQA model, it gives the correct answer 1. And now the question is, can we actually generate, again, adversarial perturbation version of this image such that it will give the wrong answer, the target answer 2? So again, here's the generated adversarial example. To human eyes, as you can see, it looks almost identical to the benign image. But however, when you feed this adversarial example to the VQA model, it gives the target answer 2. Well, clearly, you can see there is only one cat in the image. So now let's look at another example in the domain of deep reinforcement learning. Deep reinforcement learning has been very effective in training, for example, agents to play video games and also, for example, to play Go and so on. So we wanted to study whether these deep reinforcement learning systems are also vulnerable to adversarial examples. So here in your left frame, what you are seeing, these are the original frames showing the trained reinforcement learning agents to play Pong. The green panel is the trained agents. As you can see in this frame, that the agent actually has been trained very well and plays very well. So in the middle frame, you are going to see these are the original frames with adversarial perturbation added to it. And the adversarial perturbation added to it is so small that, again, to human eyes, you can't tell the difference to the original frame. But however, what you can see here is that the same agent which played really well in the original frame, which reaches max reward, when it's playing the game with adversarial perturbation added to it, it fails completely and reaches the minimum reward. Again, this is an example demonstrating that adversarial examples can also be very effective to domains such as deep reinforcement learning. And the examples I mentioned so far, these are in what we call white box attacks, where the attacker actually knows the details of the neural network architecture and the parameters. Our work and also other researchers' work have also shown that adversarial examples can also be effective in even settings such as black box attacks. In black box attacks, attackers actually don't have details of the neural network, such as the architecture and also the parameters. However, our work and others' work have shown that even in such settings, attackers can still generate very effective adversarial examples to fool the learning systems. And also what I have shown you is just the tip of the iceberg. And in general, this is a domain called adversarial machine learning, about learning in the presence of adversarials. And adversarial machine learning can happen at different stages of learning. One is at inference time, where, for example, attackers manipulate inputs to the learning system to try to fool the learning system to give the wrong answer, such as the adversarial examples that I have shown you. Attackers can also attack the learning systems at the training stage, where attackers can try to poison the training data set, for example, by providing poison labels for some of the data points to fool the learning system to learn the wrong model. Overall, adversarial machine learning is particularly important for security-critical systems. Given its importance, numerous defense and detection mechanisms have been proposed. There have been hundreds of papers on arXiv in the last couple of years proposing various different detection and defense solutions. However, today there's still no sufficient defense. With strong adaptive attackers can easily evade today's defenses. Overall, I strongly believe that security will be one of the biggest challenges in deploying AI. And hence, we really need to explore new methods to improve the security of the learning systems. When we talk about security of learning systems, there are several different levels for security at the learning systems. First is at the software level. At the software level, essentially, we want to ensure that there are no software vulnerabilities, no traditional software vulnerabilities for these learning systems, such as buffer overflows or access control issues. And the goal for this is to prevent attackers from taking control over the learning systems through exploiting software vulnerabilities. Even though this is still an important area with open challenges, however, at least in the security communities, we have had decades of experiences and with techniques and tools developed to address this issue. The more important and open questions for security of learning systems lies at the learning level. And then there are a number of challenges for security at the learning level. So one, we need to evaluate systems under adversarial events, not just normal events. This is similar to the distinction between regression testing versus security testing in traditional software systems. In traditional software systems, we do regression testing where we run programs on normal inputs with the goal to prevent normal users from encountering errors. But however, it's also important to do security testing, which is to run programs on abnormal adversary inputs with the goal to prevent attackers from finding exploitable errors. When we try to evaluate learning systems, we also need to differentiate between regression testing versus security testing. So for most of the machine learning papers, when you look at the experiment section, essentially we are doing regression testing, where we are trying to test the learning system on inputs which have similar distribution to the training distribution. However, when we try to evaluate the security of learning systems, it's important to do security testing to try to test the learning system on abnormal adversary inputs to estimate the resiliency of the learning system against adversary inputs, similar to the adversary examples that I have shown, for example. Another challenge for security at the learning level is that we need to be able to reason about complex and non-symbolic programs. In general, we are familiar with symbolic programs such as operating systems, file systems, compilers, web and mobile applications. For these symbolic programs, semantics are defined by logic. And we have decades of techniques and tools developed for logic and symbolic reasoning. And we essentially have entered into the era of formally verified systems with different formally verified systems, including microkernels, file systems, and many others. And largely thanks to the formal verification tools and the dedicated teams in the last decades. Even though for symbolic programs, there's still a lot of open challenges for being able to reason them, but at least we've had decades of techniques and tools developed for logic and symbolic reasoning. But however, when we are dealing with learning systems, we are dealing with non-symbolic programs where we don't even have precisely specified properties and goals. For example, when we want to ensure that a self-driving car does not drive over a pedestrian, We don't even have a precise mathematical definition of what a pedestrian means. And hence, and also we don't have good understanding of how the learning system works. And unfortunately, most of the traditional symbolic reasoning techniques do not apply in this domain. And I would say that for security of the learning systems, this is one of the biggest open challenges, is how we can actually even help specify the desired security properties and goals, and to develop effective techniques to enforce them. We also have other challenges. Another challenge is how we can define new architectures and approaches with a stronger generalization and the security guarantees. And due to time limit, I won't have time to go into the details. I just wanted to briefly mention one of our work as one example of a first step towards this goal. So this example is in the domain of neural program synthesis. And again, I won't have time to go into the details. But the goal of program synthesis is to teach, for example, is to build these neural program architectures and to train it to perform certain program synthesis tasks to teach computers how to write code. And so far, there has been several challenges for this neural program synthesis. One is that it's difficult for them to generalize. For example, when you train, in this case, addition program, the addition problem with input length of, let's say, 10 digits, and when you test for inputs of 30 digits, the learning program may give you the wrong answer. And also, even when in the tests, the learned neural program give you a correct answer, but still there's no proof of generalization. So in our approach, we introduce recursion to neural program architectures and learn recursive programs. And our work showed that by introducing the notion of recursion, we can help the neural program architecture to learn and generalize faster. And also, for the first time, we can provide proof of generalization to to ensure that the learned neural program architecture, neural programs actually can have perfect generalization. And the work has won the Best Paper Award at ICLR earlier. And there are a number of lessons that we have learned from this work. Is one, program architecture impacts generalization and probability. And recursive and modular neural architectures are easier to reason, prove, and generalize. And our work has shown how to provide generalizable solutions in a specific domain for neural program synthesis. And it's important for us to explore new architectures and approaches to enable stronger generalization and security properties for broader tasks. And another challenge is how we can reason about how to compose components. As we build large, complex systems, it requires compositional reasoning. And the question is, how do we do abstraction and compositional reasoning for non-symbolic programs? The list of open challenges is actually very long. And besides the challenges at the learning level, there are also challenges at the distributed level. For example, how do we make sure that as each agent makes local decisions, how we can ensure that good local decisions can achieve good global decisions. So far I've talked about the first part, how we can, how attackers can attack the integrity of the learning system and what we can do about it. And the second aspect is how attackers can attack the confidentiality of the learning system. And due to time limits, I won't have time to go into the details. So one thing I just wanted to quickly mention that in one of our recent work, we demonstrated that neural networks actually can really remember training sensitive information in the training data, and attackers can exploit this to extract the secrets in the original training data from just simply querying the learned models. And in this example, we show that when we train a language model, where the original training data set contains actual users' credit card and social security numbers, attackers can actually, by just querying the language model, be able to automatically extract the original social security number and credit card numbers that were in the original training data set. And this is an example illustrating that even as we as we train machine learning models, it's really important to pay attention to protect users' data privacy. And luckily, in this case, that we are able to provide a good solution, which is to show that instead of just training a vanilla machine learning model, if we train a differentially private language model, then in this case, we can still have good utility, and also at the same time, we can significantly enhance the privacy protection for users' data in this case. And again, I won't have time to go into the details for this. And in our recent work, we also showed that how we can develop a type system to enable us to automatically verify that a learning algorithm and implementation is differentially private. And this won the Distinguished Paper Award at the top programming language conference. And finally, I just wanted to end that data is critical to the modern economy, but however, data security and privacy are really important. And it's important for us to build a new platform for a responsible data economy that actually help users to maintain control of their data and also at the same time to enable data to be utilized in a privacy-preserving way. And at Oasis Labs, we're actually trying to build this new platform for a responsible data economy. And we have collaborations and pilots run at Stanford hospitals, and also we are working on launching a new service to enable users to maintain control of their genomic data. So to summarize, there are many open challenges at the intersection between AI and security. How to better understand what security means for AI and learning systems, how to detect when a learning system has been fooled or compromised, how to build more resilient learning systems with stronger guarantees, and how to build privacy-preserving learning systems, and how to democratize AI. And the work that I have shown are collaborations with my great students, postdocs, and other collaborators. And overall, again, I strongly believe that security will be one of the biggest challenges in deploying AI. It requires a community effort, and let's tackle the big challenges together. Thank you.
All right, so I'm going to ask a question. So thank you for the great talk. I was wondering how much does the black box nature of deep learning models add to the complications around security and privacy, and how much do you think the recent advances and methods in explainable and interpretable AI is or would be helpful for those challenges?
Okay, thanks. That's a very good question. Right, so partially how these, why these learning systems are so easily fooled is that we really don't understand actually how these learning systems really work. And the explainable AI and these type of approaches definitely can help us to try to better understand how these learning systems work and help us to find better solutions that provide greater resiliency against attacks for these learning systems. However, one thing I would like to mention is that we still have a really long way to go for providing explainability, interpretability for these learning systems and to try to understand how these learning systems work. So for example, our work and others' work have shown that many of these interpretability and explainability methods actually themselves can be attacked by adversarial examples. For example, it's very easy for attackers to attack the attention mechanism and so on. So overall, these are still very important open questions, and we still have a long way to go.